So, in the name of Allah, the most merciful and most beneficent, let us start our beginning discussion of today's class. In previous class, we discussed two things. One was some special functions like the gamma function and the beta function and its related properties. And whole of this lecture series is available on YouTube, everyone knows. And in the second part of that lecture, we discussed Laplace transform. So what we discussed was very fundamental, and we are going to do the remaining things today. The first thing that we discuss is what is the definition of Laplace transform. So this is, let us recall what we did. So given f of t, where t is greater than or equal to 0, then the Laplace transform of f of t is defined as f of t is the function that is given to us multiplied by sub kernel e power minus st, and this integration is done on this domain 0 to infinity, and we call this particular thing to be a function of s. So this is the definition, and the domain is from 0 to infinity, and the reason behind this is this t shows time. So time mostly runs from 0 to infinity and it goes ahead. And when this f of t satisfies certain properties, then we call that this particular integral converges. Then the Laplace transform of that function is going to be capital F of s under certain conditions. And one thing else, that this s can be real or complex, but in our context it is mostly real. But if the condition is applied that it is a complex number, then the real part of that complex number should be greater than some fixed value. Sometimes it is greater than 0, sometimes it is greater than some other fixed value. So let us say it is greater than some fixed c. So this is the definition of Laplace transform. And what is the kernel of this integral transform? The kernel is e power minus st, because we know very well integral transforms for any function f is defined as integral on some domain, maybe 0 to infinity or minus infinity to infinity. So generally I am writing a set A and f of t and some kernel dt, and this is going to be some function of s, let us name it f hat of s. So this particular function k is called the kernel of integral transform. So this was the definition of Laplace transform, and we discussed Laplace transform of some elementary functions. For example, number 1, Laplace transform of t power n is going to be n factorial divided by s power n plus 1, where n is going to be any natural number 1, 2, 3 and so on. And we can generalize this particular thing as well. When n is not a natural number, it is something else, then this thing should be what? Laplace transform of t power n, s power n plus 1 remains n. What is going to be n factorial in the form of gamma function?
Gamma n.
So it's going to be gamma of n plus 1. Gamma of n plus 1. Because you know very well that gamma of n plus 1 is n times gamma of n using the recurrence relation, and gamma of n is going to be n minus 1 times gamma of n minus 1, and this goes on, and this right hand side becomes n factorial. So when this thing is valid, gamma of n plus 1.
For positive?
Yes, it is valid for
positive integers?
positive and
0.
it means one thing is that this n plus 1 should be greater than 0. It means n should be greater than minus 1. So this is valid when n is greater than minus 1. it means this n should not be minus 1. If n is minus 1, then this becomes 1 over t, and Laplace transform of 1 over t does not exist. We know it. This is valid for these conditions. Okay, we did some other Laplace transforms as well. For example, what is the Laplace transform of this exponential function? That is 1 over s minus a. And again we have to apply this condition that real part of s, so if this s is a real number, so real part is going to be s itself should be greater than this a. Then this particular integral for this Laplace transform converges. And I am not restricting this condition by looking at this integral, this particular function, but this condition comes from the convergence of integral. You put this function over here and you say that this particular integral converges subject to this condition. So this is the condition for the convergence. Similarly, what is the Laplace transform of sin 80? That is a over
S square minus
a square
plus
plus a square.
plus S.
And number 4, what is the Laplace transform of cos 80?
S upon S square plus
S upon s square plus
A square.
a square. And the next thing that we did was number 5, Laplace transform of sin hyperbolic AD.
A upon
Same, but
without
this plus would be minus.
minus
So a over s square minus
A square.
a square, and Laplace transform of cos hyperbolic AT is
S upon
s upon s square minus
A square.
a square. And we can find out the Laplace transform of any function which is simply the linear combination of these all the functions. Because we know very well that any integral transform is a linear transform, or in other words we can call it it's a linear function. It's a linear operator. So for example, I am given a function f1 of t and a function f2 of t with some constants, let's say alpha 1 and alpha 2, and I am going to find out the Laplace transform of this whole. So this will be alpha 1 times
Laplace transform
Laplace transform of f1 of t,
plus
alpha 2 times Laplace transform of
2 of t.
f2 of t. So for example, I am interested in this one, Laplace transform of t plus sin 2t. So this is going to be Laplace transform of t
One upon S
plus Laplace transform of sin 2t. So this becomes 1 over
S square.
s square plus
2 upon
2 over s square plus
4.
2 square, that becomes 4. So we can apply these things because every integral transform is a linear transform. So we can apply these properties. Okay, and another thing that we discussed so far that is also available in the lecture videos, that when f of t is of exponential order, then we can find out the Laplace transform of those functions, and this is what we call the necessary condition or the sufficient condition for the existence of Laplace transform. Okay, so let us go ahead.
एक्सक्यूज मी
Sir,
यो जब तक आना रियल पार्ट लिखे हुए जो
जी
यो फिक्स्ड हूँ दो फिक्स्ड में पॉजिटिव भी थी सके कुछ भी थी सके
but I am saying that this integral converges subject to this condition. The real part of this s should be greater than something. For example, I am saying that Laplace transform of e power at is 1 over s minus a. Now, this result is equal to this result subject to this condition, otherwise not. Otherwise, I cannot say that this is equal to this.
थैंक यू
So, sometimes, as already discussed, in any MCQs test, they ask us for calculations, for definitions, for theorems, for different ideas, and some questions may be related to simple common sense. We have discussed in the very first lecture. So we'll be discussing some theorems as well. There is a theorem that says that how is the behavior of f of s as s goes to infinity. So can you tell me from these examples that in this particular function when s goes to infinity what happens?
This 0.
0.
Approach to 0.
S goes to infinity, 0.
0 also.
S goes to infinity, this becomes 0. S goes to infinity, 0. And here, what about this?
Again 0.
Same 0.
0.
మొత్తం S మొత్తం ఇయ్యాలి.
S is here as well.
S is increasing precisely.
Yes.
Therefore,
So you have to see that which one is increasing fast. The denominator. So denominator increases fast and denominator goes to infinity. So the whole result will be 0.
0.
So it is indeterminate form. You can apply L'Hopital rule or some other things. You can check the result. So this is particularly the behavior of f of s. When s goes to infinity, this is going to be equal to 0. Or it means we can say that this particular Laplace transform of any function goes to 0 as s goes to infinity. And we can prove this thing as well, and even we have checked this thing that why it happens. Why is that so? So how can we prove this thing if we are going to the proof? Any idea about this?
Generator of the limits use करना. General form वाली.
Yes, yes. First the thing is that you integrate any function and you integrate the absolute value of the function. So you integrate absolute value of function, you integrate a function and then take its absolute value. Which one is going to be smaller? This is the main result in real analysis. So you integrate a function, then take its absolute value. You take your function, take its absolute value at every point, then integrate. This thing will always be smaller than or equal to.
This condition hold for any function, you mean?
For any function. For any function which is integrable, Riemann integrable. Otherwise we can't apply this condition. We'll be looking at this result when we are going for what we say real analysis. There are some remaining things. You can compare this thing with sum as well. You take the sum of a function from, let's say, I runs from 1 to n, and you take its absolute value. It will be less than or equal to. Take the absolute value at each and every point, then add them. And we call this thing to be triangle inequality. This is triangle inequality. For example, I am restricting this n to 2. Then what happens? This is going to be f1 plus f2, its absolute value. First add, then take absolute value. And what is this thing? This is first take absolute value, f1, then add. And what is this called?
Triangle.
Triangle inequality. So I have triangle inequality, I am extending it to any fixed n, then I can extend it to infinity, and if I am converting it to integral, this will look like the same thing. So this result also holds. So I know very well that f of s is 0 to infinity e power minus st f of t and dt, and I am taking absolute value on both sides. Then I claim that sometimes it is very easy to see short proofs. It will help you to memorize the things or keep the idea of the things in your mind. So this thing will be less than or equal to, I am taking the absolute value of the integrand. What is that? E power minus st f of t. We discussed that this thing is always less than this thing from the previous example that I have written so far. But you know very well the absolute value of exponential remains same. Can you tell me why? It means this is absolute value of the product of two functions. Then what can I do? I can take the absolute value of this one and the absolute value of this one. But the absolute value of exponential remains same. Because exponential function is never negative. Absolute value gives us the positive result. But if the function is already positive, you can't do anything for that. Now you have this thing. But Laplace transform exists for the functions that satisfy this condition. We know very well. The functions of exponential order. We discussed in the previous class. If the function is bounded by exponential times a fixed constant, we call this function to be of exponential order. For such a functions we can find out Laplace transform. Otherwise we can't find. For example, I give you this function e power t square. You cannot find out the Laplace transform of this function. Because e power t square cannot be bounded by this e power ct. Whatever value of m you take. Okay, so I will replace this function. I will say that this function is less than m times e raised to ct and dt. And you know very well this is a constant, I can take it out and this thing becomes what? Plus ct dt, is it okay? Is it okay up to here?
Yes, sir.
Okay, why am I doing this? It should be equal here. So, what is this integral? Just what I have to do, I have to write e power
Oh, you word you को later is.
minus s minus c times t dt, and I am writing the integral finally. You integrate and you evaluate this thing, this whole thing becomes 1 over s minus c. And when s tends to infinity, what happens? 0. So when s tends to infinity, this particular thing becomes 0. So absolute value of f of s is less than 0. So what about this particular function? This is absolute value, means always positive. If a positive thing is less than or equal to 0, it means the thing must be 0. So that's the proof. So I am not taking any particular function. I have taken a generalized function, that a function that satisfies this condition. For this theorem holds. Otherwise we could take a particular example as well. So it is not necessary to keep the proof in your mind, but at least theorem should be there. Proof was very simple, that's why I did it, otherwise I was not supposed to waste time.
So t square वाला थोड़ा ये समझा लो मत ही जो example यो नतो थी जो
Sir, e power t square cannot be bounded by this function because the power of e is a linear function in t here and the power of e is a quadratic function. Now you say that okay, I take the value of m to be very very large in billions trillions. Still there would be a time when this function will cross this one.
Yeah,
The time will come when this function crosses that one.
मतलब rapid change है.
Yes, that's the thing. That's it. We discussed some inverse transforms as well, but we will be doing these things later on because inverse transforms are not that much necessary because we are just inverting these formulas that we have so far. But at least we should know the basics that okay, if I have inverse Laplace transform of let's say a over s square plus a square, then it is going to be sin 80 because I know very well that Laplace transform of this thing is going to be this one. So for example, I am given 1 over s square plus let's say 9. So what can I do? I can write this as Laplace inverse of s square plus
3 square.
3 square. So I must have 3 here.
3 here, yes, sir.
So what can I do? I am multiplying 3 and dividing
3.
3. So this is going to be sine 3t. So we can just reverse the basic formulas that we have so far. The rest of the things remain same. Okay, so the next thing is what are the transforms of derivatives? Transforms of derivatives. These things are very much important when it comes to solve differential equations with the help of Laplace transforms. So, what is the Laplace transform of f prime of t?
S of f of s minus
Yes.
0.
So, it is going to be the Laplace transform of the function without prime is going to be f of s, multiply it with
S
s and minus f of 0. This is what? This is capital F. So this is the Laplace transform. And what is this? This is the value of this function evaluated at 0. We call this initial condition.
Yes, sir.
Similarly, what is going to be Laplace transform of f double prime of t? That's going to be f of s. Here the power of s is 1. Here it's going to be
S square.
s square. And what about the rest of the terms?
Minus f dash of 0.
Yes.
minus s
So
dash
S of 0.
the first thing is that this is s square.
Yes, sir.
Then I have to write a polynomial in s. Polynomial in s. It means I have to give s power 1, then I have to give
0. Yes, sir.
s power 0. What should I multiply with s power 1?
F dash of 0.
F of 0 or f dash of 0?
Dash of
dash
dash of
It means one of these is going to be dash and one is going to be the simple.
Yes, sir.
Which one is dash and which one is simple? And this is going to be dash and s power 0 is 1, so I can simply remove this thing. And I can remove 1 as well. So this is s square times f of s and the rest of the things is going to be a polynomial in s.
Yes, sir.
If this is s square, this will be a polynomial of degree 1 because that's the s square. And what are the coefficients? The coefficients are these initial conditions. F of 0 and f prime of 0 and f double prime of 0 and so on. And these initial conditions come from the initial value problem that is given to us when we solve a differential equation. Similarly, if we generalize this thing, what happens? Laplace transform of fn of t. So that's going to be f of s times
Yes, sir.
s power n and then
Yes, sir.
sn minus 1 f of 0 minus sn minus 2 f prime of 0 minus and so on up to finally f of 0. I am mistaken.
F dash of 0 and last.
No. This is the inverse. This is f prime of 0 and this is f double prime of 0
9.
and this is n minus 1 derivatives. So this is in that way. And what is the logic? Let me tell you. What is the power of s? N minus 1. How many times it is differentiated? 1. 1 and n minus 1, their sum is n. What is the order of the derivative? 2. What is the power of s? N minus 2. So n minus 2 plus 2 becomes n. So this total sum is going to be n. This is just the logic behind this.
What about last one, sir?
Then there is a problem with that. N minus 1 f of 0. Yes. This is f of 0. This is f prime of 0. This is single prime. So their sum is going to be n minus 1, not n. Sum is going to be n minus 1. Now we can apply these things to solve differential equations. For example, solving an initial value problem. So the problem is, let's say, dy by dt plus 3y equals 13 sine 2t, and the condition is given to us is y of 0 equals 6. What is the benefit to apply Laplace transforms to solve ordinary differential equations? We can solve partial differential equations as well. We have the Laplace of these derivatives, and this is simply a derivative, but the function is y, here the function is f. It doesn't make any difference. But what is the benefit to apply Laplace transforms as compared to the ordinary method that we have so far? You can say the left hand side is order 1, but it can be a differential equation of order 2, order 3, and so on. We can apply Laplace transforms on these other things. The main thing is that when you solve these equations, you do two things. You find complementary function, you find particular integral. When you are done with both of these things, you apply initial or boundary conditions to find out the values of arbitrary constants. It means there is a stepwise process. But here you can do everything in just one go.
One step.
Yes, just apply Laplace transform, put these conditions, and you are done. So there is no complementary function, there is no particular integral, there is no arbitrary constant, so they put the value and get the answer. There are no things like that. So what you can do, you can apply Laplace transform on both sides, dy by dt plus 3y equals Laplace transform of 13 sine 2t. So dy by dt, the Laplace transform is going to be, you can consider this is y prime of t. The Laplace transform is going to be s. Let's say this is capital Y of s. Laplace transform of y of t is capital Y of s minus y of 0. This is f of 0, this is y of 0 plus Laplace transform of y. It's a unknown function, so I will write y of s because it's a unknown function. 13 sine 2t, it's 2 over. Now what happens that Laplace transform transforms your differential equation into an algebraic equation. This is an algebraic equation, there is no any derivative. First find the value of y of s and then apply inverse Laplace transform. You're done. So what am I going to do now? This y of 0 equals 6. That's given to us. So I am taking these two terms and I am taking y of s common, and the right hand side is going to be 26 over s square plus 4, and I am taking this minus 6 here, it becomes plus 6. So y of s is going to be 1 over s plus 3 because this will be 1 over, and let me add these things. So this will be s square plus 4 and 26 6s square 50. So then I have to find out the inverse Laplace transform of this particular thing, and I am done. But the problem is, the main problem is how to invert this. Otherwise the rest of the things are going to be very much easy. Yes, and for this we know the basic tricks that how to deal with this thing. So y of s is going to be 6s square plus 50 over s plus 3 and s square plus 4. Now the inverse Laplace transform on both sides, will give me y of t here, and here I have to find out inverse Laplace transform by reducing it into partial fractions and applying inverse Laplace transform, and then I am done. So let me write this. So this is going to be 8 over s plus 3 minus 2s over s square plus 4 and plus 6 over s square plus 4. So inverse Laplace of this is going to be e power minus 3t,
Yes, sir.
because 8 is outside, e power minus 3t for this particular function,
Okay.
and for this one minus 2 s over s square plus 4
Cos.
cos 2t,
Yes, sir.
plus this is going to be 6 common, and for this I need 2,
Yes, sir.
so divided by 2
2 multiplied.
sin 2,
Sin 2t. Yes, sir.
and then this thing becomes
3 sin 2t.
3 sin 2.
Okay.
Yes, 3 sin 2t minus 2 cos 2t. Yes, that's the answer. So it took just only 5 minutes to solve this equation, but the main idea was not to just do this problem, but to tell you that why we are doing this thing and why it is necessary to apply Laplace transform and what are the problems when we apply Laplace transform. The first thing is that you have initial condition, it is directly involved in your problem,
Yes, sir.
and you don't find complementary function and particular integrals for this. This is a first order, you don't find complementary and particular, but I am just giving this example to save the time. The next idea is the equation becomes an algebraic equation, not a differential equation for now.
No.
Solving it for y of s and inverting it will give us our result.
Yes, sir.
So that's the idea behind this.
अच्छा सर ये जो सेकंड लास्ट स्टेप है यहाँ से आपने पार्शियल फ्रैक्शन की है
Yes, partial fraction. वो तो हो जाएंगे.
आराम से
Everyone is good at
Convolution theorem with
convolution theorem. Yes, we can apply that.
यार बार बार इधर
That would be problematic.
yes, sir. Yes, sir. Partial fraction is yeah.
तो थोड़ा ये रटा याद हो जाए
ये पार्शियल फ्रैक्शन तो ये सही है
ना वो रिजल्ट में लिखे ना
हाँ
लैपटॉप पे याद नहीं चाहिए
Okay, so the next idea is just you take these things and write the formulas and theorems on a single page. For one subject, it will take just 4 to 5 pages. That is enough for the preparation. So here we are going to discuss because everyone gets to know the things. So the yes sir.
इनिशियल कंडीशन अगर ना हो जाए डिफरेंशियल इक्वेशन थी लैपटॉप ट्रांसफर अगर लगे हो मुझे
Yes, you will write C as a constant
सही है
and just to apply the same process.